Welcome back. The next speaker is Professor Xiao Xiong from Harbin Institute of Technology, HIT. So the title of his talk is Function Spaces on Quantum Theory and Their Applications. So let's enjoy.
Okay. Firstly, I like to thank the ICBS organizer for the award, as well as for giving me this opportunity to share my paper and also some other works related to this paper. So the first part of my talk would be the spaces, function spaces, and quantum theory, and then the second part I will give two applications about this function space theory. Okay, so our motivation to developing this function space theory was that we were trying to seek for ways to define noncommutative spaces so that we can do some more analysis and even some other geometry or even pseudo-differential operator, PDEs, something like that. Okay, let's begin with the integration. So if we have a polynomial algebra, then we can define a trace. This kind of trace is an abstract version of some integration in a functional analysis way, because the conditions here are just all fulfilled by integrals. So here, the first one is additivity, and then the linearity, and this is the tracial property. And if we have a polynomial algebra, and then when we have a trace, we can define the LP spaces. So this is kind of the abstract version of the classical measure theory, because in the classical case, when we have a measure, then we can look at the space of essentially bounded functions. But now bounded functions are replaced by a space which is called polynomial algebra, and the trace, the integration is replaced by trace. So that's why we call this noncommutative LP spaces. Okay, let's look at the quantum theory or noncommutative theory. So basically, let's just look at the definition. It is a C-star algebra generated by some operators. But if we look at the degenerate case, which means that our theta becomes 0, then this UK and UJ, they are commutative. In this case, we can just consider this C-star algebra as the continuous functions and classical D-torus, because in this case we can just put UK as the function e to the periodic function e to the xj. So here, with this in mind, we can also look at the polynomials, which is the sum of this u to the power m, and also so this is the definition of the u to the 2 pi to the power m. And also, if we go back to the classical torus case, this u to the power m is nothing but a periodic function e to the 2 pi I x dot m. Okay. So here we can have a trace, so which is nothing but the coefficient alpha 0. This is just you can you can understand this as that when you do the integration to the classical functions and torus, then you will get nothing but the constant coefficient. So this way we get a very good functional, which is linear, positive, normalized, faithful, and trivial. So in this way we have a system algebra, and also we have a good functional plays the role of integration in this system algebra. And now with this, in this case, we can do the GNS representation, and then we take the Weierstrass closure. So now we will get Von algebra. Here I denoted as T theta D. The Von algebra plays the role of the O infinity and classical T theta D. So now then we have a noncommutative probability space, or even called quantum probability space. So here is a dictionary, a correspondence between classical LP spaces and non-commutative LP spaces. And classical tori, this is a probability space, and the algebra is commutative, and the integration is with the higher measure, and this is LP. Everything is well understood. Now in the quantum tori, we have so-called quantum probability space and some non-commutative algebra, and integration is replaced by trace. And same, we can still use this trace to define LP spaces. Okay, so now we are able to consider the bigger spaces. But if we want to move further, we need some other structure to define other function spaces. So let me first introduce the Fourier series, Fourier multiplier, Fourier coefficient of the functions, or even for the operators. So every operator which is integrable admits a Fourier series. So also the Fourier coefficient is the integration of u to the power m dot take the joint times x. So this Fourier coefficient. Also, if you look at the classical torus, if you are given a function, then you multiply with e to m dot x, then you take the integration, and you got the coefficient. So at least formally we can look at the Fourier multiplier, which is also in the classical torus. When you Fourier multiplier is that you take the Fourier transform, and then you get to the ZD side, and then you multiply with a function, and then you do the Fourier transform back. So this is at least formally we can define like this. And also, if we have a function on Euclidean space, we can do the convolution. But still, we can understand it as a Fourier multiplier. So here are some other structures. Here are some other structures about quantum torus. So firstly, we like to select some very good function, which is smooth functions and quantum torus. And then on this smaller setter, we can define the partial derivatives like this. So here, either you can understand this partial derivative as a very special Fourier multiplier, or you can just go back, look at the classical torus, because in the classical setting, as I mentioned, this function or this operator, this function uj is nothing but the function e to the I xj. So then in this case, if you take the derivative with the jth variable, then you get uj itself. But if you take the derivative with the other variable, then you will get 0. So in this way, you have the definition of partial derivatives. And which one? Mm-hmm. Uh, yeah, yes. So this is Schwarz class. Yeah, and and also next is we look at the topological dual of this Schwarz or this linear space, because we can have some topology here, Frisch topology, and we look at the dual of this topological linear space, we get the distribution. Okay, so also we can define this Laplacian, which is the negative operator, and the spectrum is also the numbers 4 times pi square times the modulo of m squared. So here, I still like to introduce more very special very special Fourier multiplier. The first one is raised and Besov potential. Well, in the classical case, we can define this as from the singular integral theory. But now we can also view it as Fourier multiplier. And also we have a way to define Littlewood-Paley decomposition on T and Littlewood-Paley decomposition. The idea is that we look at the Fourier transform side, the frequency side of our operators or functions. So this Littlewood-Paley decomposition requires a function which satisfies this kind of identity. Okay, so with this we are able to move forward to give the definition of Sobolev, Besov, and other spaces more than LP. So Sobolev spaces for Sobolev spaces we look at the partial derivatives of operators. But here I didn't mention that, but it can be done in the very classical case that we didn't define this dm to the distributions, but we can define it using the duality. Yes. No, dm, yeah, dm. I can go back. Yeah, dm is this one. Yeah, sorry. I just mentioned that we have. Yeah. Okay. So this is Sobolev space, and this is fractional Sobolev space or potential Sobolev space, which which is given by functions such as that the alpha order potential belongs to LP. And Besov space is that we fix some phi, we fix some phi, which satisfy the very good condition I mentioned last page. But we will see that the definition of the spatial space doesn't depend on the spatial phi we fixed. Okay. So from this page, we don't see any difference between the functions on quantum torus and the functions on classical torus. But for Hardy space or for this kind of Triebel-Lizorkin space, which can be viewed as extensions of Hardy space, they are quite different from the classical Hardy space. So let's first look at the definition. Still, we look at distributions, but here we take the square or every convolution, and then we take the square root, and then we take the p norm. So here I have 2 points I want to emphasize. The first point is that in the classical Triebel-Lizorkin space theory, there are 2 indices, p and q. But q would be here. Q is the q power of this absolute value. But now in this case, we are not able to define it for arbitrary q. The q must be fixed as 2. The reason is that here inside this p norm, inside the p norm, this is not just functions, not just scalars, but here we have operators. So that means that for q doesn't equal 2, this is not even a norm, because the triangular inequality doesn't hold in that case. So now we can just fix the q as 2, so which is omitted here. So q is always 2. This is the first point I want to mention. The next point, the second point I want to mention is that we have this kind of column and this row, and then this mixture. This is also new in the quantum case. The reason is that the column and row, so for the same operator, the column norm and the row norm will not equal, not even equivalent. You can easily have counter examples such that the column norm is small, but the row norm is very large. So this is one reason we have 2 versions. Another reason is that if you know a little bit about the classical Littlewood-Paley theory, the LP norm of a function f would be equivalent to this kind of this square, the LP norm of this square function. But this is based on the classical Kinchin inequality. But in the noncommutative case, if we want some kind of Kinchin inequality, you must have you must look at the norm like this. So for example, if p smaller than 2, the single column norm or the single row norm will not equal to LP. So here they are quite different from the classical case. Okay, So now we have the definitions of these functions. So next, you may ask when we after defining these spaces, what properties they will have. So then that's the next part of my talk. So how can we do the analysis on these function spaces? The first tool I want to mention is that we strongly rely on Fourier multiplier theory. So here I have a theorem which is very important to my next conclusions. This theorem states that the completely bounded Fourier multiplier on LP space of quantum tori is exactly the same as the completely bounded LP Fourier multiplier on classical torus. So here I've not spent time to explain why here we need to look at completely boundedness, because but let me just show some examples of these completely bounded spaces. The first example is that if we have a measure which is a Fourier transform of L1 function, then we have a Fourier multiplier which is completely bounded. This is the first example of a Fourier multiplier. And the second example is the very famous Harman-Miklin type Fourier multiplier. Well, this is but in this case, P should be strictly between 1 and infinity. This is this you can view this as the vector valued Harman-Miklin theory. So with these two conclusions, we are able to transfer most of the classical inequalities to the current setting. So for example, when we look at the equivalence between this potential Sobolev space and this Sobolev space, then we need to have two inequalities. This one is larger than this norm, and the converse is also true. So this equivalence can be reduced to the boundedness of some very special Fourier multiplier. So this is the first conclusion I'd like to say. But here, P should be strictly between 1 and infinity, because here there are some kind of hormonal type in Fourier multiplier. And also for the second one, for the relation between Sobolev space and Besov space, the inequalities here is also some kind of boundedness of some Fourier multipliers, and the others two are the same. And also the lifting property here, we need to look at this operator, which also can be reduced as, can be viewed as Fourier multiplier. The next result is about characterization. So what I just mentioned is that my function phi in this definition is some very special function. But if we replace the function phi by some other function psi, c, then we need to have some equivalence here. The equivalence of the boundedness here also comes comes from the boundedness of some Fourier multipliers. So this is the reason why I put this kind of a requirement on the kernel side, because I need these conditions to ensure the boundedness here. And this is the discrete version, and here the bottom one is the continuous version. And so let me introduce the second tool, which is the semigroup tool. So remember that my condition here is even though it looks very complicated, but it can be fulfilled by the kernel of these semigroups. So for example, if we want to know that the Besov norm of an operator is equivalent to the semigroup, and then to this formula, then we just have to verify that this kernel, this function, satisfies the condition I required in the last slide. So with this characterization, we can use some properties of this semigroup to do some other analysis. For example, the very important one is the Sobolev inequality. Well, this is our Sobolev embedding. This firstly we have this embedding for Besov spaces, because now we have this equivalence. Then we are able to use the ultra contractivity of this semigroup to get the Sobolev embedding. And for the critical case, we are able to show that this Besov space be the critical case. Here 1 times d equals d, and here d over p times p also equals d. This is a critical case. It will not belong to be emptied to L infinity, but to BMO, to a space or with some cancellation property. I will not go into the details, but here we can prove both of this inequality by using semigroup method. The third one is kind of easy to understand, which is interpolation, because at least the interpolation series was first constructed for spaces, for Banach spaces. But here all these spaces are Banach space, so we can use this very easily. So for example, potential Sobolev space, and this is the complex interpolation, and this is the real interpolation. And also the last one is the K functional, which is the K functional for real interpolation method. Sorry? Yeah, yes, that's, yeah. This, yes. So here this was this one. I didn't give the definition, but this one is the divide difference of x. Yeah. So in some case, like this is Lipschitz. Yes, exactly. Yeah. And indeed, we can show that the Sobolev space is the Sobolev norm is equivalent to some kind of Lipschitz norm or some other spaces like the Zygmunt spaces. Okay. So the last result on my first talk is the Sobolev embedding inequality. So in the very classical case, if you know well about the proof of Sobolev inequality, you may know that the first case we dealt with is the W11 case, because in this case we can have some real method to prove that the LD over D minus 1 norm is smaller than the one of the Sobolev norm. But so far in the quantum torus case, we are not able to prove that stronger inequality. This is a weaker one. So this Sobolev space is embedded into weak LP. The reason is that we use interpolation in the proof, so we were not able to deal with the endpoint case. So we have interpolation between 1 and infinity. This is easy, but if we want to know the Sobolev embedding inequality, we have to use the real interpolation, so that we can get the strong inequality for Sobolev spaces. But this cannot be used for endpoint case. So that's why our result is a little bit weaker than the pointwise case. Okay. So next for the next time, for the remaining time, I like to give 2 applications. The first one is application to pseudo-differential operator theory. So let me introduce a little bit the definition of pseudo-differential operator theory. So suppose that we have a function which is very smooth function, rho, and suppose that this function, I like to say that here we have a variable psi, which is inside the Euclidean spaces. But okay, so then we take the derivative with this real variable, and also we would like to know the derivative differential with respect to with respect to the quantum tori. So this I define this as d theta. This d theta is nothing but the previous d, because now I have 2 different derivatives. I like to distinguish to make the notation clear. Okay, so here is the condition. Here's the condition I put on my symbol. If you know if you know a little bit about classical pseudo-differential operator, you must know that the symbol is has 2 variables, but now I have only 1 variable, and this RD. The reason is that in the quantum case, I don't have a function, but I have operator. So that means that if I fix a psi of this variable in RD, then I get a rho psi, which is still an operator. In the classical case, my rho for a fixed row, for a fixed psi, this row psi is still a function. So this is the reason why I have only one variable. I have only one variable. The other variable is operator, hidden in the operator. And so this is the definition of symbol. And, and this formula gives the definition of pseudo-differential operator. And also, if you know a little bit about classical pseudo-differential operator theory, you may know that this is defined by oscillatory integration. But I just use this very different formula, which is just formally defined as the Fourier series of our function. So still here, for every m, this row m could be a scalar, but also could be an operator. So in this case, we can understand the pseudo-differential operator as the combination of Fourier multiplier and pointwise multiplier. Because if rho always takes value of scalar, then this one is Fourier multiplier. But if this rho doesn't depend on m, which means that this rho is a constant function. Is a constant function, then but takes value in some operator here. Then you can put rho outside. Then it is a pointwise multiplication. So indeed, even in the very abstract case, you can understand pseudo-differential, understand zero-order pseudo-differential operator as the C star closure of Fourier multiplier and pointwise multiplier. So this is an abstract, a C star way to understand the pseudo-differential operator. Okay. Our result is that for good data and for good indices data and rho, our pseudo-differential operator is bounded on Sobolev space, Besov space, and here, if you don't like this alpha, it is local Hardy space. Local Hardy space. But there is an example that this is a case which is called the forbidden case or singular case, which is that this delta and rho both equals 1. Then in this case, this p rho, this pseudo-differential operator, is not even bounded on L2. So this is a singular case. So in this case, we have to put some positive order alpha, and then we can show that this pseudo-differential operator is bounded on positive order of Sobolev space. Okay. So this is the first application. Here I have some remarks. Let me go through the remarks very quickly. So can we do further for this kind of pseudo-differential operator? The first setting is that we can look at the operator value setting, which means that our function is the function takes value in some Banach space. And then the symbol must take value in the linear operators of Banach spaces. So this is first setting. But maybe if the next setting is, I think is more interesting. if we have a system action on some system algebra, then we can define the pseudo-differential like this, pseudo-differential operator like this. This was indeed the original definition of oscillatory integration. This would be another extension of pseudo-differential operator, and indeed I know some group is studying this case. Okay, so the next application is about noncommutative geometry. So the setting is that we have a Fredholm module, unbounded Fredholm module, or in other words, we have a spectral triple. The definition of spectral triple, I think, goes back to Alan Kohn, who wanted to recover the algebraic covariance by the spectral triple. That should be the original motivation of this Fredholm module. This Fredholm module consists of an algebra and a representation, and then an operator, which is the abstract elliptic operator. This operator should satisfy that the commutator between the elliptic operator with the elements in this algebra is compact. It's compact. So why it is compact? Because in the operator setting, compact means small. Compact operator means it is a very small operator, because outside a finite dimension subspace, the operator is very, very small. So with this in mind, you may, if you are given variable, then if you define the derivative, then you must have infinite small. So with this in mind, we may say that this is a quantized derivative of some variable or some operator. Okay, so knowing that compact operators are small operators, we must want to know that how can we measure the size of this infinite small. So the way to do it is that we look at the singular values or eigenvalues of the operator. So for example, the eigenvalue is of finite support. We know that T is finite rank. If it is LP summable, then we call this Shelton SP. We don't even have to know about this, but we just keep in mind that we are talking about the size. We are talking about the size of the compact operator. Okay, this is the setting. So then the quantized differential is the derivative. Is the commutator of this abstract elliptic operator with the element in the algebra. And the integration is given by Dix-Meer trace. It's given by the Dix-Meer trace. I will not go into the details of Dix-Meer trace, but I just want to mention that this Dix-Meer trace vanishes on any infinite small operator, which whose order is larger than 1, and also vanishes on S1. So that is the abstract setting of quantum derivative. But when we look at our concrete case, this f is given by the simple Dirac operator. Dirac, which is the, so here d is the square root or Laplacian. D is the square root or Laplacian, which is derivative, which is Dirac. And then we take the functional, the simple calculus to get this form. So here gamma j is just something already appear in the Dirac operator, because when we take the square root of Laplacian, we are not able to take the square root of Laplacian. But if we have this gamma j, we have this polymatrices, we are able to. And then when we take the functional calculus, this, if you're familiar with harmonic analysis, this is nothing but Riesz transform, one very special singular integral. So in this setting, so this is the last page on my slides. So in this setting, we are able to determine the size of a function, or a smooth function. So here, if p is larger than d, then it is non-trivial commutator. But if p is smaller or equals to d, then d must be a constant. So here is the cutoff. And also the last result is trace formula. So let's look at, let me explain a little bit about this trace formula. So the left-hand side is the Dixmuir trace of the commutators, and the right hand is the yo-yo trace and quantum derivatives of this yo-yo derivatives and operators. So in this is here we have this is equality. So this equality tells us the way we transfer classical integral or classical differential forms to the quantum differential by the quantum integration or quantum differentials. Here we must look at the Dixmuir trace of the operators. In this way, we find the connection between classical and quantum. Okay, sorry, I use.
Many thanks to Professor Xiong for his wonderful talk. Any question or comment? Okay. Yeah. Any other question or comment?
I just have one quick question. And when you do this non-commutative integral, you use a trace.
Yes.
So for the trace, of course, say tor and tor xy is the same as tor yx. Do you think something really non-commutative, like you do a positive linear functional instead of a trace?
Well, if this trace is some kind of weight.
Yeah, if it's a weight.
Well, then the problem, the situation becomes very bad. Yeah.
It's bad.
Yeah, it's bad. For example, if we look at some type of spray phonema algebra, which we don't have a trace or tracial weight, then then the analysis there is very, at least the Zeno is very difficult. Yeah, but basically, when we talk about trees, when we view these trees as the noncommutative extension of integration, usually we have this tracial property. But yeah, but if we don't have this tracial property, then at least most of my result here, we don't know how to do it.
Thank you. Any other question, comment?
So can you construct differential forms over the quantum torus? So not only functions, but also differential forms.
Mm-hmm.
So you construct the forms already?
Yeah, differential, yeah.
You have this, I guess one need a cyclical homology to construct differential forms. So do you just use analysis? You can.
I think this was part of the motivation when Alan Kohn looked at this. Yeah, part of the motivation was that people can look at the RTR single index theory. In that case, the at least for quantum torus, the differential forms is what I define in this setting. Is the die J. We have K. We have yeah.
That's differential.
Yeah, that's a differential form.
So what is the degree of the forms?
I don't know. Yeah, but I think yeah, I know less about this.
I guess it's better to stop here, and let's thank our speaker again.
Thank you.